me try to draw the phasor diagram for this situation here. So phasor diagram, again, you start by drawing the x and y axis. You will not need to label the x and y axis because the x and y axis, they are not representing anything. They are just trying to split the space into 4 quadrants. The first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. Okay, so we know that there's a resistor and there's a capacitor. So let's try, the first thing that we can do is we can fix a current at a specific angle first. Then after that, only we draw the potential difference. So did you see my usual work? I've been labeling my current at the positive x direction. That's because that's where time is equal to 0. Of course, you are free to choose any other direction for any other angle for our current phasor. Okay, but I'll draw it here because it's the usual way of drawing it. Okay, so I call this one I0 because that's a phasor for my current. First, you fix that place for your current because later when you draw your voltage phasor, you have to draw it with respect to the current phasor. That's why you always start with drawing the current phasor first. Okay, so once you have done drawing the current phasor, what we draw next is the voltage phasor. But there's two circuit elements involved, so we have to draw 2 different voltage phasor, each for 1 circuit element. So the easiest one will be the voltage phasor for the resistor. So the voltage phasor I'll draw in purple, so that will be in the same direction as the current. Why is it in the same direction? Because it's a resistor. So resistor, the voltage and the current should be in phase. So if in phase, the phase angle should be 0 degree. So I will call this one V0, the peak voltage for resistance. You can find it using I0 R. Okay, so that's for our voltage phasor for resistor. How about the capacitor? We know the capacitor, the voltage lags the current by 90 degree. Okay, so if it lags means by it is running, catching, it is trying to chase from behind. So this should be the angle of the voltage phasor for capacitor. So the voltage, peak voltage for capacitor is equals to I0 1 over omega c. Of course, the whole discussion here is equivalent if you are trying to talk about it in terms of RMS. So of course, you can also say this is VRMS for resistor, which is equals to IRMS across the flowing through the whole AC circuit times R. And of course, you can also talk about this whole relationship here. For capacitor, it will be VRMS for capacitor, which is equals to the IRMS flowing in the AC circuit times the reactive capacitance 1 over omega. So if you want to be extra clear with everything, you can draw here. Then you can see this is 90 degree. Okay, so that's the phasor diagram for this AC circuit over here. So essentially what we do here is we have been merging together the phasor diagram for pure R circuit and pure C circuit. For pure R circuit, the phasor diagram is something like this. For pure C circuit, it will be this I and this V over here. Okay, so what we essentially do is we merge them together under the same current phasor. Okay, so what's the purpose of doing that? If you want to determine the RMS value of the sinusoidal voltage, that's the overall voltage, right? So overall voltage, how do we do it is by finding the vector sum of the 2 voltage. Because overall means by, if you are doing a normal, let's come back to DC to make it make sense. If you're doing a normal DC circuit, then you probably have one resistor and another resistor connected in series. Okay, so essentially what you usually do when you're doing a DC circuit is you will sum up the resistor over here and the resistor over there. So when you do V equals to IR, then your R essentially is just R1 plus R2, right? Well, you can't do that for this situation. You can just take R plus C in this case. Okay, then you sub it inside for this R. No, because if you see here, the V for capacitors and the V for resistors are not in phase actually. So if you want to add them together, you have to involve some kind of vectors. Okay, so how do we do that is, okay, if you are doing it for DC circuit, right? So for DC circuit, then you will add on another resistors like that. Then this one will be, you have this one as R1, you have this one as R2. Then you can just add up the VRMS for R1 and the VRMS for R2, then you get the VRMS for overall. But that's not what we are trying to find here. We are trying to find for a resistance and a capacitor. So this is slightly intricate and it involves vector sum. So if we talk about vector sum, I believe you have known sufficiently about vector sum that you can deduce that the overall voltage later will be pointing somewhere here. Why do I say somewhere over here? Because that's, if you sum out this part and this part, you will get an angle which is somewhere around here. Okay, so this will be the V0 for the overall circuit. So V0 for overall circuit, we can just call it as V0. And this V0 will be equals to I Z, where this Z is called an impedance. Okay, we'll look more into impedance in the next slide, in the next video. But for now, you need to know that if this is V0 for the overall circuit, or for the whole AC circuit, then you know that the relationship between V0 and I0 is called impedance. Okay, the ratio of V0 to I0 is called impedance. And of course, the ratio between VRMS to IRMS, you can also call it as impedance. So that's for the overall circuit, the AC circuit. So if you want to find the VRMS for the overall circuit, you know that you requires to add these two things to sum up them, but sum up them is not a direct plus. You require the use of Pythagoras theorem. Okay, so it's just finding the hypotenuse of a triangle actually. So let's try and put this into calculation. To determine the RMS value of the sinusoidal voltage using Pythagoras theorem, we find that VRMS for the overall circuit will be equals to, so it will be a vector sum between the RMS for R and RMS for C, the voltage. Okay, so it will be VRMS for resistance square plus the VRMS for the capacitance square. Then square root it, then this Pythagoras theorem will tell you the hypotenuse, the length of the hypotenuse, which is essentially just the length of the V0 phasor for the overall circuit. So from here, we can do a bit of substitution. VRMS for R, we have determined from question A that it's 60 volts, 60 volt. For capacitance, it's 100 volt. So if you do this calculation, you find that the calculation is essentially just 116.6 volt. Okay, so that's how you determine the RMS value for sinusoidal voltage. You use Pythagoras theorem. Okay, the next thing is they ask for the impedance. Impedance, from what I see just now, is just the ratio between VRMS and IRMS for the overall circuit. So if I write down a relationship over here, I'll find that impedance here is just VRMS divided by IRMS. So if I do my substitution, the VRMS for the overall circuit is 116.6. Our IRMS, it's given in the question just now, it's 5.0 milliampere. So if you calculate everything, I think you should get the answer of 2.33 times 10 to a power of 4. So what unit should you give? Again, this is V divided by I. So V divided by I, you know from Ohm's law that it will be, in DC, Ohm's law, that will be resistance, which is in the unit of ohm. So for here it's also V divided by I, so we can use the same unit. So the unit will be ohm. So this is the impedance. So you can think of it like the resistance version in the whole AC circuit, the effective resistance version in AC circuit. But it's actually called the opposition of the overall opposition effect of the AC circuit. Okay, we don't call resistance because resistance is R, right? Call it opposition. Okay, but essentially it's just the ratio of V to I for the overall circuit. So to determine this impedance, there are also other methods as well. If you can see from this working that we did over here, you see that Vrms here is equals to I RMS Z, whereas Vrms R is I RMS R. Vrms C is I RMS 1 over omega C. What's in common between these three terms over here is that all these three terms have I RMS in it. So actually there's something that we can mess around with to find a new way to obtain impedance. So let's try and figure it out. We know that Vrms is equals to Vrms R square plus Vrms C square. So again, we say just now all of them have IRMS in common. So let's break it down in terms of IRMS. So this is IRMS Z. Then this will be IRMS. Then this will be R. Then they will both be squared. Then you have IRMS. Then you have 1 over omega C squared. Okay, so what's interesting over here is you're actually able to factorize out IRMS over here. So you can get IRMS square, then essentially what's left is R square plus 1 over omega C square. So for here, I believe you know that we can break these two parts, this square and this square, into two under separate square root roof. So essentially you can have IRMS square, then you have square root of R square plus 1 over omega C. So I think you know where am I trying to go. What I'm doing right now is I'll be cancelling out the IRMS on both sides. But before that, let me just write it down really clearly so you know how it goes around. So now this will be IRMS. Then this will be R square plus 1 over omega C square. So now you can see that there's IRMS on both sides of the equation, so you can cross it out. And now we'll be left with the equation of the impedance. So impedance is just equivalent to the Pythagoras theorem. Then you are having R square plus 1 over omega C square. So just to recall, 1 over omega C here is representing the capacitive reactance. So it's you're adding up the sides of a triangle, which one side represents the opposition effect due to the resistor, the other side represents the opposition effect due to the capacitor. So you are adding them up using Pythagoras theorem to find the magnitude of the hypotenuse of the triangle. So I believe if you substitute the same thing as what we obtained in the question, you know that R is 12 kilo ohm square and plus 1 over omega is 100. Then you have your 0.5 micro. Maybe if you square them all together, you get the same answer as 2.33 times 10 to the power of 4 ohm. Okay, this working over here is showing us that the phasor diagram can be re-expressed in a different manner. So we can still have our current pointing in this direction. But what's different right now is instead of having Vrms for resistor and capacitance, what we can have is we can have the resistance in phase with the current, the resistor, It's not that the resistor is a changing phasor. It's just to show that the resistance is aligned with the current vector, whereas this capacitive reactance here, it's 90° away. Okay, it's just to show that these two things can be calculated in another way. So this is xc, which is equals to 1 over omega c. Then you find a Pythagoras theorem between these two things, the r and xc. Then what you get is you get z over here. Okay, so that's the idea of re-expressing this phasor diagram in another form. But just to take note that this r here actually is not a phasor because it does not rotate with time. The same thing with this omega c here, 1 over omega c here. This 1 over omega c here does not rotate with time as well. This is not exactly a phasor diagram, but it's just there to tell you that this thing, this capacitive reactance and the resistance, you can obtain the impedance by finding the hypotenuse side of the triangle formed by the resistance and the capacitive reactance. Okay, so it's not exactly a phasor diagram, but it's just another way of representing the idea. The last thing that we have is find the phase difference between the current and the applied voltage. So the phase difference that they mentioned here will be the phase difference. If you look at the phasor diagram, it will be over here. So to obtain the phasor diagram, to obtain the phase angle, what we can do is we can do inverse tangent. So this is similar to all the vector sum that you have done before. So if take the y divided by the x. So it's just the inverse tangent of the RMS voltage of the capacitance, but this is with negative because it's going downwards, divided by the RMS voltage for the resistance. Okay, usually when we do inverse tangent, we usually put a modular sign, right? Most of the time, in previous chapter, we usually just do a modular sign over here. But for this case, I don't really put a modular sign here because the negative and the positive sign in the phi here actually carries a meaning. That's why it's quite important that we leave the negative sign there. Okay, and we don't need to have modular sign because we don't want just the absolute value of the angle. We want the sign of the angle as well, whether it's a positive phi or a negative phi. That is important as well, so we cannot just remove the sign as we wish. Okay, so now if we sub in all the values, then you have inverse tangent. VRMS for C should be negative 100. VRMS for R should be 60. So if you calculate all these things, I believe you should get the answer of negative 59°. So this negative 59° essentially means that the V is actually lagging the I. The V is lagging the I by 59°. Okay, but if you are asking for phase difference, just writing it like that should be enough already. Okay, so that's all for this question.